Don't hang up that phone. We've found what you're looking for. Welcome to the 5 Minutes with RCDD podcast. Well, seeing how we're pulling Category 6A, the most powerful twisted pair in the world, you gotta ask yourself this one question. Did I pull 295 or 300 feet? Well, do you feel lucky? Do you, punk? In this podcast, you'll learn the differences between a 66 and 110 punch tool, the proper way to install a support cable, along with terminating and testing parameters. What exactly does RCDD stand for? Really can't do diddly? Or just some guy that's just sitting around in a chair making podcasts. So join us as we talk about the ever-changing world of telecommunications, from ISP to OSP, from copper to fiber, design to installation. Now send the new guy to the truck for a bucket of dial tone and the cable stretchers, while you listen to an informative program on telecommunications. Here's your host, Chuck Bowser, RCDD.
Welcome back. Glad to have you here 5 minutes with an RCDD. This is the conclusion of our 3-part series of megahertz versus megabits. In the first of our series, we discussed bits and bytes. You remember those, the ones and the zeros? From there, we moved on to the sinusoidal wave and encoding schemes like return to zero, non-return to zero, and Manchester to explain how we organize all those ones and zeros. This episode, we finish off that series and apply it to cable. Now for today, we're going to focus primarily on copper cable, since that's still the most commonly used cable type for cabling for network cabling. I remember back in the good old days, we used to put in what was called POTS cabling. We'll talk more about that here in a minute. So back in the first of the series, first things we covered was, we talked about communications. What is communications? What are the 3 components of communications? Remember, you need a transmitter, a receiver, and some kind of a pathway between those two. Now, in our example today, our pathway is cable. That's what transports those ones and zeros between the transmitter and the receiver. But a pathway is not just a pathway. There are different varieties and different levels of quality. It's all based on the construction of that cable. Right? The better the pathway, the more information that can be transported down that cable consistently. That's the key, consistently. Now, just again, analogy here, right? If you're driving down a 4-lane highway and it's asphalt, and then all of a sudden you turn off to a different highway, it's 4 lanes as well, but it's not asphalt, it's gravel. Are you still going to be able to travel the same rate of speed on a gravel road? Well, and not damage your car? Of course not. Not the same person would do that. So a cable is the same kind of way. I mean, they're all kind of similar, but they're built differently to handle different types of speed. So what we start off with is, what exactly is a cable, right? I hear this all the time. I used to work with a guy. He always referred to it as Cat5 wire. Cat5 wire. That always rubbed me wrong. I don't know why, I just did. But I looked on Wikipedia, because, you gotta go to the internet to figure out what's what, right? So I went to Wikipedia and looked up the definition of a cable. And it basically says a cable is defined as an assembly of multiple wires running side by side or bundled underneath a jacket, which is used to carry electrical current. Beautiful. So that 2-conductor cable we used to use for the old NBI systems was a cable. The old Jake cable, which was 4-conductor. Remember that one? Black, yellow, and I can't remember the 2 colors off the top of my head. It's been too long. That's a cable. But the most common type of cable that we use now, the most common type horizontal cable that we use now, is a 4-pair cable. Now, horizontal cable is just a term that we use in the industry to describe the cable that goes from the telecom room, i.e. the TR in ICT lingo, acronym world, through the ceiling or through the floor or through some pathway to get to that faceplate that's on the wall. That is called the horizontal cable. I'm not sure how they came up with that, but when you look at it, even though it is a horizontal cable, it can go vertically. So they're just using that to describe that one particular cable. It basically goes from that connector on the faceplate, up the wall, through the ceiling, back to the telecom room. That's the horizontal cable. Generally, 99.9% of the time, especially if it's for a voice or data network and they are following the standards, it's going to be a 4-pair cable. What that means is when you strip off the jacket off that cable, you're going to find 4 distinct pairs. You'll find a blue pair, an orange pair, a green pair, and a brown pair. So there's basically 8 conductors underneath that jacket. So they color code those so we know which order to terminate them. I just kind of gave you a hint on them. Blue, orange, green, brown, slate, white, red, black, yellow, violet. Sorry, I went through the 25-pair color code there. So we use that color code to identify which conductor gets terminated in sequence. Now, ironically, the equipment doesn't really care what color the jacket is. It'll work no matter what way you terminate as long as you're consistent on both sides. Meaning, if you're running a cable from a patch panel to a port on a faceplate, if you put the orange-white conductor on pin 1 on the patch panel, and you put orange-white on the pin on the connector on the faceplate, and then match all the others all the way through, it will work. It doesn't care about the color. The whole reason for the color code is so there's uniformity and consistency between installers. Now you're probably thinking, why does that really matter? It matters because typically the people installing the cable are not the service technicians who will be going there to fix the cable when there's issues over the lifespan of the cable plant. By the way, the average lifespan of a structured cable plant, 7 to 10 years. Now that doesn't mean the cable just goes bad all of a sudden. What that means is the bandwidth that we're going to be needing for computers 7 to 10 years from now, we'll need more bandwidth than the cable we're installing today. That sounds like job security to me. I kind of mentioned this before. I'll say it again because it's worth repeating. When I first got in this industry back in 1982, yes, 38 years, wow. I heard from day one, copper cable's dead, it's going away. Here we are nearly 4 decades later. What are we still installing? Copper cable. But not all copper cable is the same. When you actually look at the conductors, when you strip off the dielectric off the conductors, there's a solid copper conductor underneath that. That solid copper conductor can be a couple different gauges. It could be either 22 gauge, 24 gauge, or 26 gauge. The gauge that the manufacturer chooses is to help determine on what is trying to be used for that cable. Right? For example, if you're doing power over Ethernet and you're doing, for example, like a camera, and the camera has a pan, tilt, zoom motor inside of it, the best cable for that is going to be a category 6A cable to handle the high bandwidth and a 22 gauge conductor, which will hand that electrical load for the motor. Now, let's say you got another camera, but this one doesn't have a pan, tilt, zoom motor inside. It's just a camera. It doesn't need that big conductor. It can use with a smaller conductor, but it still needs to be a good rated category cable to handle the bandwidth of that video signal. So the size of the conductors, a lot of people don't know this. They just don't really think about it. But so the 3 most common are 22, 24, and 26 gauge. A 22 gauge conductor is bigger than a 26 gauge conductor. I know you're thinking, well, Chuck, 22 is a smaller number. It should be a smaller gauge. It's not the way that it works. The smaller the number, the larger the conductor. And the reason for that is it's how they manufacture cable. When they manufacture a conductor, a communications conductor, that conductor starts off as a 5/8 inch thick copper conductor, this big, huge coil. I did a tour at the Berktech plant once. So they put that wire and they put it through this machine. And if they're making a 22 gauge conductor, they put in 22 draws, and every time that conductor goes through a draw, it bends it and puts pressure on it, enough that it actually reduces the outside diameter of the conductor by 20%. So they put in 22 draws to get it there. If they're making a 26 gauge conductor, then they put in 4 more draws. And because it went through 4 more draws, it's 20% smaller for each draw that it went through. That's why it's an inverse relationship. And they call that the American wire gauge. So what does it really mean? A 24 gauge conductor, the wire diameter is 0.0201 inches in diameter. 26 is 0.0159, and 28 is 0.0126. So as you can see, it gets smaller as the number gets larger. Copper network cables with a smaller gauge are typically available in longer lengths because they offer less resistance and allows that signal to travel a little bit further. Now we all know the whole 295 feet for maximum length for permanent link, but in the real world, if you put 10 base T Ethernet across that, which is a really old archaic Ethernet type of architecture, one we used back in the 90s, and you put it over a category 6A cable, you can exceed that 295 and it will still work. Now the problem is when you test it with a tester, it's going to give you a failed test result. So the length is generally associated so the maximum bandwidth can go across it. The maximum bandwidth we can put across a copper cable right now is 40 gigabits per second. So that's where that 295 comes from with Cat 6A cable. Generally, the more bandwidth that you try to push across the cable, you have to change the construction of the cable in order to get it to perform better. That's why when you look at Cat 5e cable versus Cat 6a cable, other than the size of the conductor, one other thing that you will notice is the Cat 6a conductors are twisted a lot tighter because they're operating at different frequencies. More on that in just a minute. So for a short recap, again, we have those 8 conductors inside of that 4 pairs, and if we put the signals on all 4 pair at the exact same time, how do we keep those signals from interfering with the pair laying right next to it? Right, we do that because as the energy goes down that cable, it creates an electrical field around those conductors, and it superimposes signal on any adjacent pairs. Well, the way that we reduce that, by the way, that's called crosstalk, and that's an old term from coming back in the old telephone days when you could pick up a phone to call somebody and you could actually hear somebody else talking kind of faintly. That was called crosstalk. So somewhere those 2 pairs were close to each other and one was superimposing its signal on the other. That's the term crosstalk. So how do we eliminate crosstalk inside of a cable? They do that by twisting those 4 pairs at different rates. So next time you get a 4-pair cable and you open up, I want you to do this. Look at those 4 pairs and look at the twists per inch. You will notice a distinct difference. The more twists per inch, the more protection from EMI. The less twists per inch, the more prone it is to EMI. EMI is electromagnetic interference. Again, that's what causes near-end crosstalk, far-end crosstalk, alien crosstalk, power sum near-end crosstalk, power sum far-end crosstalk. All those really are is just EMI. That fancy name, that fancy acronym, is just telling you where the interference is happening so you can go fix it. For example, near-end crosstalk. Near-end crosstalk just means how much one pair interferes with another pair at the near end of the cable. So the blue pair is interfering with the orange, or the orange is interfering with the green. Far-end crosstalk is how much one pair interferes with another pair at the far end. Now the power sum crosstalk, the power sum near-end crosstalk, and the power sum far-end crosstalk is how much the 3 pair inside that cable interfere with that last remaining pair. One's at the near end, one's at the far end. Again, the reason that's important to us is because in today's environment, the 40 gigabit per second lands, we're using all 4 pair. Back in the old 10 base T days in the 90s, early 90s, we were only using 2 pairs. That signals was coming across pins 1, 2, 3, and 6. Now we're using all 4 pair. So we need to know how those 4 pairs interact with each other, how they interfere with each other. So before I get and talk about how we put different amounts of data down a cable, we got to do a short recap. Now, if you want the more in-depth conversation about this, go back to the 2nd episode. We got to talk about that sinusoidal wave again, just for a brief sec, for those who may not have listened to episode 2 yet. So the sinusoidal wave is basically a rise and fall of power. Because remember, we're talking about alternating current. So if 0 is your baseline, when you rise up to the maximum positive voltage, it'll peak, and then that voltage will fall. It'll come down. It'll go through the 0 point all the way down below to the maximum negative voltage, and then turn and come back up. When it reaches that 0 line again, that is 1 cycle, 1 hertz. If it does it in 1 second, it's called 1 hertz. But again, if you want that more in depth, go back to that second episode and listen to it more. Now let's just say for demonstration purposes that 1 cycle equals a 1 or a 0. Now, remember, the second episode we talked about coding schemes, explaining how we can put more 1s and 0s on 1 cycle, but I'm just making the math easy for everybody today. So 1 complete cycle, 1 hertz, is either a 1 or a 0. So now let's talk about our cables. Now, category rated cable has been around for a long time. And you would think that we'd start off with category 1, but we didn't. The first category rated cable was category 3 cable. The predecessor to that was POTS cabling, which stood for plain old telephone service, or what some old telephone guys used to call Jake cabling. It was a 4-conductor. It was black, yellow. I can't remember the 2 other colors. You'll see them in some old houses and stuff, but you don't see them installed in commercial office buildings anymore. So I guess that would really be the Cat 1 and the Cat 2, but they didn't really label them that. So the first one was Category 3 cable. So we have Category 3, Category 5E, Category 6, Category 6A, and Category 8 in the United States. Outside of the U.S., when you start talking about the ISO standards, there's a Cat 7 and a Cat 7A. I'll talk about that here in a second. So what does that really mean? So a Cat 3 cable has a performance of 16 megahertz, abbreviated MHz, megahertz. 1 megahertz is 1 million cycles in a second. So if something's operating at 16 megahertz, that means there's 16 million 1s and 0s every second. Now, Cat 5e is 100 megahertz. So for every second, there's 100 million 1s or 0s. Cat 6a is 250 megahertz. Cat 6a is 500 megahertz. Cat 8 is 2000 megahertz. So the more megahertz, the more information it can carry. Again, simplifying it way much, because with encoding schemes, there's more than one or 0 on one sinusoidal wave. But just to kind of bring this point home. And let's talk about Cat 5e. A lot of people get confused about Cat 5e. I'm not sure why. Well, I know why. It's because of manufacturers and marketing. Because there's a Cat 5 little e and a Cat 5 big E. What does that really mean? Well, when you look in the standards, the ANSI standards for North America, there's only one Cat 5e, and it's rated to 100 megahertz. Some manufacturer, they made their cable just a tiny bit better, and so they call it Cat 5 big E. So it performs a little bit better than Cat 5 little e, but as far as the standards are concerned, it's still a Cat 5e cable. But because it has a different frequency rating, it can handle a little bit more information. Now, when you get into Europe, you get into the UK, you can find Cat 7, Cat 7A. Now, Cat 7 is good to 600 megahertz. Cat 7 is good to 600 megahertz. Cat 7A is good to 1000 megahertz. So when you compare that to what we have, so Cat 6A is 500 megahertz, it can do a 10 gigabit per second LAN. Well, that's the maximum that Cat 7 can do. So why would you choose Cat 7 cable, a more expensive cable, than the Cat 6A cable? And one of the reasons that Cat 7 didn't really get adopted in the US is because it has a proprietary connector that goes on the end of it. I think it's called like a GG45 or something like that. Where in the US, we use an 8P8C connector. Us old cable guys call them RJ45s. One of the things when they write the standards, they want to make sure that the cable plant is backwards compatible. What that means is, let's say you got a Category 5E horizontal cable with Category 5E patch panel and Category 5E jack. And this customer wants this data jack operational. So you go down to your truck, but you don't have any Category 5E cables, patch cords, not cables. But you do happen to have a Category 6A patch cord. So you take that Cat 6A patch cord and you plug it into that Category 5E jack on that Category 5E cable. Well, it's still always only going to perform at Category 5E because you're only as good as your weakest link, but it is backwards compatible. But with Category 7, because they were using that proprietary connector, it was not backwards compatible. Cat 7A does have a connector that's not proprietary, so it is backwards compatible. But it can only do 40 gig out to about 50 meters. Now we got Category A cable. Category A cable can go up to 2,000 megahertz, right? So it's more bandwidth. But it can only push that bandwidth out to 30 meters or 98.5 feet. Just a little bit shy of 98.5 actually. Generally, Cat 8 cable is going to be used in like data centers where your cable runs are going to be shorter. You're running them from a rack to a rack inside of a data center. When I used to evaluate the test records for contractors for warranties when they submitted for their projects to decide whether we're going to warranty that project or not, when I first started doing it, I started tracking averages of the run lengths because the test reports will give you that. And it's real easy to total them up. So over about 250,000 test results, individual test results, the average run length for a horizontal cable is about 147 feet. So if you ever have to come across that. So going back to our Cat 3, again, 16 megahertz, the maximum data rate it can do is a 10 megabit per second LAN. So if you've got like an internet thing or a thermostat that's controlled by network or something like that, it's going to be okay with that. Cat 5e and Cat 6, they both will do a maximum of 1 gigabit per second. Cat 6a will do 10 gigabits per second. Cat 8 will do 40 gig. Again, can't exceed that maximum of 295 feet for your permanent link or 328 feet for the horizontal cable, for the channel, sorry. I actually did a LinkedIn post just last week, and I asked for people's input. Why 295? I mean, I've heard lots of things over the years. I've heard people say, well, that's the average run length. Well, in order for that to be the average run length, that means people had to say they were running cables 600 feet long. I don't see that in any kind of office building. And then other people say, well, it's the maximum length it can run with CDCMA and blah, 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 blah. Got lots of good explanations, but they were all over the board. I don't know if anybody really knows the answer to that. And I'm an old cable guy. You'd think I would know that, but I don't. I have my feelings, but I can't say verbatim that that's exactly what it is. So the maximum length for the Cat 5e, Cat 6, Cat 6a is going to be 100 meters or 328 feet. You're not supposed to be using Cat 3 cable for horizontal cabling anymore, so they're not recommended. Getting into the backbones, you're allowed to go up to 100 meters or 328 feet, except for Cat 3. Cat 3, you can go up to a full 800 meters, 2,624 feet. The reason you go so much further, again, because it's very little bandwidth. Remember I told you, the more bandwidth, the shorter that run has to be. So when you go back to our cables, right? So again, Cat 5e has 100 megahertz. It has 100 million ones or zeros. And then that Cat 6a cable has 500 million. So you're getting 5 times the bandwidth. That's why the higher the rating, the more bandwidth that cable can handle. So that way you can choose the appropriate cable based on the network needs. If they're just doing emails to and fro, they're not going to need Cat 6a cable. But if they're doing video conferencing, they're doing, in today's environment, they're doing Zoom trainings and Zoom meetings and GoTo meetings and virtual conferences and stuff like that. Well, yeah, Cat 6 cable, Cat 6a cable will probably be best there. That's why the standards have adjusted the requirements over the years. Because initially, when they first came out, they used to tell us Cat 3 for voice cabling and Cat 5e for data. That's not true anymore because of things like voice over internet. Because of voice over internet and Cisco things. Because of that, they now say minimum of a Category 5e cable. But you really should put in Cat 6 cabling. In data centers, the minimum is going to be Cat 6, but the recommended is Cat 6a. So I hope you're able to glean from this why there's different ratings of category cable and why the Cat 6a cable is better than the others. If you do, shoot me a message. Look me up on LinkedIn, send me a friend request, and then shoot me a message. Say, Chuck, I got something out of that. Or if you have a question, same thing as well. Got some exciting things coming up for future podcasts. I'm in the process of working on one now for project documentation to help the lead technician or the project foreman how to document their projects in such a way that if they get taken to court, their word will be almost held like gospel. Working on that webinar next. And then I've got some great interviews lined up. I've got one lined up with one of the test manufacturers. Testing is my favorite subject, so that one's probably going to be longer than my normal podcast. Then I've also got an interview lined up with one of the people I met at the BiCSI virtual conference last week is in charge of doing the mentoring program for BiCSI. So I'm interviewing her. And then also I recently became friends with Blake, the guy who runs Low Voltage Nation. He's got a cool thing going on over there. Check him out. He's creating a community of ICT people. And we need that. It's one of the things we've always lacked. We're both doing the same thing. We're creating a community. We're just doing it a little bit differently. I'm doing it more of a mentor-mentee kind of relationship. He's doing it more of a peer-to-peer relationship. He's got some great stuff going on over there. So him and I are supposed to be doing an interview tomorrow. And then I'm going to be interviewing him for my podcast. Look forward to this great podcast coming up soon. I mentioned the BiCSI virtual conference. So last week I went to the BiCSI fall conference, and it was supposed to be held in Vegas. But they did it 100% virtually because of COVID restrictions. And when I was first told that I was going to be attending this, because I was told by my company I was going, I was like, virtually, I don't know. I've been to about 20 conferences, and I like going there. I like being face-to-face with people and meeting people. I guess that's kind of why I make a good instructor, right? Because I like talking to people. Ironically, though, if you put me in a room of unknown people and I'm not in work mode, I'm actually extremely quiet. I'm an introvert. A lot of people don't say, Chuck, oh, I don't see that in you. That's just how I am. Get me out of a work environment. I am an introvert. It's just the way it is. So anyways, I had some, I wasn't sure if this virtual thing was going to work out. Now, I will admit that there were some things that I didn't really like about the virtual conference, i.e. the face-to-face connectivity and stuff like that, but there were some things that they did really cool. For example, in a face-to-face BiCSI conference, when you're there, they like to schedule sessions concurrently. So you had to choose which one you wanted to go sit in. So if they had one on fire stopping and another one on grounding and bonding, you had to choose which one you wanted to attend because you couldn't be in two places at one time. In the virtual class, the virtual BiCSI conference, you can actually go back and watch the ones that you missed. And we have up to 30 days to watch any session that we miss. So I really, really, really like that. And then we also had, the way they did networking was they had chat rooms. They had one chat room on leading trends. That's where, if you were at the virtual conference, that's where I hung out a lot. And each manufacturer had a chat room. I spent a lot of time in our chat room as well, talking to people. So you did get some network there. Matter of fact, that's how I came across the lady from BiCSI who does the mentoring program. So that's how I set up that interview. So there's a lot of good things going on, and they're saying that the spring one's going to be a hybrid. It's going to be partially virtual and partially in person. Be really, really interesting to see. Well, that concludes today's episode, and I hope you really enjoyed this content. If you did, make sure you give us a thumbs up if you're watching us on YouTube, or give us a 5-star rating if you're listen to us on one of the podcast forums. That just helps us raise in the algorithm, get out to more people. And also, like I said, make sure you look me up on LinkedIn. I love connecting with people. The mentoring people, we selected our 2 people. They are going through the initial processes of coming into the mentoring program. One person wants to become an RCDD. The other one's brand spanking new to the industry. He just wants to achieve his first certification. So I'm helping those 2 individuals this year achieve their goals. They both asked that I not say their name, so I can't say who it is, but they are extremely excited, and we've had multiple conversations already. Looking forward to that. So until then, be safe.
That's it for this episode of today's podcast. We hope you were able to learn something. Make sure to subscribe so you don't miss out on future content. Also, leave a rating so we can help even more people learn about telecommunications. Until next time, be safe.